Good morning, people of physics, or once again, good afternoon. It all depends on your style. Hey, great to see you today. Let's think about one more round of complex circuits. Hey, we're going to use our favorite tool, Ohm's Law, a whole bunch. We're going to lean on that today. I want to remind you that the last thing we thought about was called a series circuit, right? We thought about a series circuit, and what you've seen in a series circuit is that you have one path and all the charge flows through that one path. And one of the key ideas that we picked up last time was that the current in each element in the circuit is the same, because again, there's only one route, and whatever current flows at one spot has to be the same because there's only one path. That's the story on a series circuit. Today we're going to look at a parallel circuit, a different arrangement of complex circuits. Now again, I'm drawing resistors here, these squiggly lines. It's just as easy to do the same thing with light bulbs. I mean, they mean the same thing, but resistors are easier to draw. So today I'm going to draw a parallel circuit. Same idea, we'll start out with a battery. I'll put in a single resistor, like so. But then in parallel to that, notice the two resistors are lined up along parallel lines. I'm going to add another resistor. And this is what we call a parallel circuit. Now we can add two resistors or 3 or 4 or 7 million, it doesn't really matter. They're all the same concept in a parallel circuit. But let's think about this for just a minute. If we had a chunk of charge, let's make our charge this color today, and it were to travel through the circuit. At this point right here, something interesting happens. That charge has to make a choice. That charge can't go two places. It can't be in both places at once. So as this charge comes moving around in the circuit, it's either going to go through this first resistor or it's going to go through the second resistor. In fact, I'm going to go right here and I'm going to label this I1, and I'm going to go up here, excuse me, and I'm going to sneeze, and I'm going to label this I2. Remember, I is the letter that we use for current, and we have two different branches here. So again, I'm going to name them separately just to keep things organized. This is resistor 1, and this is resistor 2, just to keep track of what's what. So let's think about what happens. This current leaves this point, comes right here and has to split, and some goes through this path and some goes through the other path. But you'll notice over here, that current comes back together again, and that current returns back to this point after going through either resistor. And by the time we get down here, what we find out is that that current is back to what it was before. I'm going to use the term I total right here to refer to the total current provided by the battery. And the neat thing to notice is that if you take the total current and you compare it to what goes through resistor 1 and resistor 2, well, because of these two little spots right here where things split and then come back together, we know that we have to take the current through 1 plus the current through 2 to get the current total. This is a neat idea. It just says the current from the battery splits up into multiple routes. Notice how that's different than in a series circuit where the current's the same everywhere because there's one path. So in a parallel circuit, the idea is that we don't have one path, but we have multiple paths. So that's the key difference, is one path versus multiple paths. Now we got to have a little nameology going on here. These things I referred to with the circles, those are called junctions, as in a place where things come together. So there's a junction there, there's another one over here. Those are both called junctions. And the point to think about with a junction is that we'll have current coming into a junction, and then we have a split. And the idea is to think about this total current coming in, and the idea that it tends to split into pieces. And that's where this equation comes from. And in fact, it's where we come up with a concept that is known in the physics world as Kirchhoff. That's a person's name. Kirchhoff's junction rule. And Kirchhoff's junction rule is nothing more than a fancy name for what we already talked about. The idea that the current coming into one point goes out from that same point, and whatever comes in has to equal what goes out. In fact, if you really want to think about it, it's a conservation of charge idea. But bottom line, what you need to worry about today is just the idea that the total current is equal to the current at one spot plus the current at another. Now, what does this mean practically? Well, let's flip back and think about how we could tackle some problems. First off, if you look through the chapter, section 2, you'll discover a pretty good description of these ideas, and I would encourage you to do that. So if you go to section 14.2, there's a really nice description of what is a parallel circuit. There's a description of Kirchhoff's current law that you see right there. And then there's a little bit of work with Ohm's law and how we deal with circuits in parallel. And the problems that I'm going to ask you to experiment with today are just that. Let me just take one and walk you through it. But the good news is you can use Ohm's law, and as a result, I think you'll find you are in pretty good shape on this idea. So let's take a look at the problems. So in the problems that you'll see today, you'll notice that there are parallel circuits lined up like so. And you'll notice in these parallel circuits, we have a battery and we have some resistors. And these happen to be the same resistance in some cases, but not in others. Let's just think about how that might work. So let's take ourselves a parallel circuit and let's experiment a little bit. And I wanted to help you to recognize that as long as you're comfortable with Ohm's law, you are golden on parallel circuits. So here is a battery. And let's take a couple of resistors and we'll throw them up here in parallel. And let's take our battery and make it, how about 20 volts? And let's take this first resistor and let's make it 5 ohms. And let's take the second resistor and we'll make it 10 ohms. One of the neat things to recognize about parallel circuits is that if you measure the voltage, it's the same everywhere. Key idea, if we were to take a voltmeter, I suppose we should use the FET-sim here, but if we were to hook on a voltmeter on the battery, you would find out it would say 20 volts. But if you took that same voltmeter and you hooked it up, all right, so let's put our voltmeter on here. Hey, it's going to read 20 volts. Let's put our voltmeter up here across this resistor. Well, it's going to read 20 volts again because you notice these sides are connected. They're effectively the same place. And I just scribbled on my drawing, sorry. All right, and again, the same idea. If you put a voltmeter on the second resistor up top, you'd continue to see the same thing. That is, anywhere you stick a voltmeter on here, you're going to get 20 volts. So one of the neat things about a parallel circuit is that the voltages are the same everywhere. Notice that's not how it was in a series circuit. So let's get to the point. Let's ask ourselves the question, what is I, the current, at each resistor? Well, if we take Ohm's law, rearrange it and solve it for I, we get V over R. So if we think about the 5 ohm resistor, well, the current in it is V over R. The voltage, 20 volts, divided by the resistance, 5 ohms, well, 20 over 5, hey, that looks like 4 amps. So we'd have 4 amps of current flowing in this branch. If we do the same thing for the 10 ohm resistor, well, same deal. I is V over R, and V is 20 volts, and R is 10 ohms. Hey, 20 over 10, that's 2 amps. In other words, we've just identified that going through this branch is 4 amps. Going through this branch is 2 amps. And what does that tell us about the current that would be traveling back through the battery, or the current provided by the battery? Well, the total current is just the sum of the individual currents. So the total current, of course, in this case is just going to be 6 amps. How about that? So that's the concept using Ohm's law with this new idea of parallel circuits and practicing a little bit with some problems. So I'm going to ask that you work through that section review today. There's a few problems built in, and I can't lie to you, that is going to be just about our last problem set. We might have a couple other little ideas to explore, but that's the key. Please stop in with some questions. Please practice those problems, talk to each other, see how they go, and recognize that you are almost done. Way to go. Thanks, folks. Have a great day.